You feel it every day. It rustles the leaves, whips your hair, and can even tear down fences. It's an invisible force, constantly shaping our world. I'm talking, of course, about the wind. But have you ever stopped to think, why does the wind blow? What invisible mechanics are at play, orchestrating this constant movement of air? To understand wind, we first need to understand something fundamental: air pressure. Think of air not as empty space, but as billions upon billions of tiny molecules zipping around. These molecules, just like anything with mass, are pulled down by gravity. They also bump into each other and into surfaces, creating a force. That force over a given area is what we call pressure. Imagine a tightly packed room. Lots of people, lots of pushing. That's high pressure. Now imagine a practically empty room. Not much bumping. That's low pressure. And here's the key. Nature hates imbalances. It always tries to equalize things. And that, my friends, is the fundamental principle of wind. Air always moves from areas of high pressure to areas of low pressure. It's like water flowing downhill, or a compressed spring releasing its energy. The greater the difference in pressure, the faster the air moves, and the stronger the wind. This difference in pressure is called the pressure gradient. A steep pressure gradient means strong winds. A gentle one means light breezes. But what causes these pressure differences in the first place? The number one culprit is heat, or more specifically, uneven heating of the Earth's surface by the sun. Think about it. When you heat air, its molecules get more energy. They move faster, they spread out. This makes the air less dense. And less dense air rises. As it rises, it leaves behind an area of lower pressure. Conversely, cooler air is denser. It sinks, creating an area of higher pressure. This is why we get things like sea breezes. During the day, land heats up faster than the ocean. The air over the land gets hot, expands, and rises, creating low pressure. The cooler, denser air over the ocean rushes in to fill that void. That's your refreshing sea breeze. Temperature isn't the only factor. Moisture also plays a surprising role. Believe it or not, humid air is actually lighter than dry air. At the same temperature and pressure, water vapor molecules are lighter than the nitrogen and oxygen molecules that make up most of our atmosphere. So, areas with more humidity can also contribute to lower pressure. And then there's altitude. As you go higher, there's less air above you, so the pressure naturally decreases. These pressure variations due to altitude drive larger atmospheric circulations. Now, let's zoom out to the global scale. The sun heats the Earth most intensely at the equator, creating a persistent band of low pressure as hot air rises. This air then travels towards the poles, cools, sinks, and returns towards the equator, forming what we call the Hadley cells. These are powerful engines of atmospheric circulation. But it's not just one giant cell. We have three main sets of circulation cells in each hemisphere. Hadley cells. Near the equator, hot air rises, moves poleward, sinks around 30 degrees latitude, and flows back to the equator. Ferrel cells. In the mid-latitudes, a more complex, indirect circulation, polar cells. At the poles, cold, dense air sinks and flows towards the mid-latitudes. These cells create predictable zones of high and low pressure across the globe, setting the stage for our global wind patterns. While global patterns dominate, local conditions create fascinating wind phenomena. Mountains, for instance, can drastically alter wind flow, leading to specific winds like the warm, dry Chinook winds in North America. And what about storms? Thunderstorms are essentially giant engines driven by intense pressure differences, with powerful updrafts and down. Hurricanes and cyclones are massive low-pressure systems where the Coriolis effect causes the wind to spiral inwards, counterclockwise in the northern hemisphere and clockwise in the southern. High-pressure systems, conversely, have air spiraling outwards. These systems dictate much of our daily weather, so the next time you feel that cool breeze on your face or watch the trees dance in a gust, remember the incredible forces at play. The sun's energy creating pressure differences and the Earth's rotation elegantly curving the air currents. Wind isn't just random air movement, it's a beautifully orchestrated ballet of molecules, driven by fundamental laws of physics. If you found this invisible journey fascinating, please hit that like button. What's your favorite thing about the wind? Let me know in the comments below. And don't forget to subscribe for more deep dives into the incredible science all around us. Thanks for watching, and stay curious.